Okay. All right, what are we going to do? Okay. What's that?
Why is there a calculator on the clock?
No idea. Don't really care.
I don't know that number.
Okay, so if we do the derivative of the antiderivative, we get back the integrand. We get back the original function. Okay, so this means the integral is an antiderivative of f. So remember when I say sometimes take the antiderivative or find the integral, they're, yes.
So you take a derivative of the integral, you get the function.
Yes, the derivative. So think about like multiplication and division, right? If you take a number and you multiply it by 3, and then you divide it by 3, don't you get back what you originally started with? Yes. Okay, Charlotte? Okay, so we have to introduce a new variable here. It'll make a little bit more sense when we get to future examples. Okay, we always want to make sure these two variables are the same. A is just any constant. So this is a constant. And these two variables, this one and this one, have to be the same. And then I usually just f of t dt, it doesn't really matter. It could be f of theta d theta. It could be f of w dw. You just want to use a different variable. It's kind of just like a placeholder. Yes, Adam?
Why is the area under a graph and the slope at a point the opposite of each other? What? I don't know.
It's not that simple. You're talking about two very different things. Okay, no. I don't want to get into it all, but when you're doing the derivative, you're finding a formula for the tangent line, right?
Yes.
Okay. Can you evaluate that at one point? Yes. Okay, integrals. When you find the integral of something, you're finding a formula for area under the curve, but it's not just like at one point. It's over two limits of integration that you're being evaluated. So it's, if you're just so I'll show you the proof, okay? But these two, and you'll see when we do the integral of the derivative, it'll work the same way. It'll be very similar, okay? And that's actually what we're going to do down here. So if we say take the antiderivative of a to x of f prime of t dt, I get back f of x plus some value of c, right? Do we remember how we had that plus c, that constant of integration?
Yeah.
Okay, talked about that. T is nothing. T is just a different variable because we want to have these, I could say f of w dw. I just don't want to use x. Okay, so this is what we did yesterday, right? Yes, or
where did the x come from? Isn't it supposed to be f of t?
No.
You need to put the,
these two are going to be these two are going to be the same because we're taking d dx of this function. Okay, you're asking good questions, but there's stuff that we didn't get to yet called the fundamental theorem of calculus, which is 6.4. So we will get to all the reasons why we have. You have to put the fundamental theorem of calculus in here. So there's two parts to the fundamental theorem of calculus. So we have part 1 is where you do the derivative of the antiderivative, okay? And you get back the original function. And then there's a part 2 where we do the integral of the antiderivative. The t...
It makes sense. But before you just put the f of x and you didn't count the minus f of a.
Correct. Here's why.
Like swallowed by the c.
This is the proof for it. So let's take a look. So the question was, you didn't get there yet because he knows the fundamental theorem of calculus probably. You do not. So jumping ahead. Here we go.
She knows it.
Okay, do you agree with this statement based on what I've told you? The integral of the antiderivative gives us the original function plus c. Okay, that's what we did last class. Okay, now, if I replace this and this, x here and here, with a and a, I have not done anything. I've just replaced the x with a. We're okay with that? But remember what I told you yesterday about this part? It's 0, right? Because the limits of integration are the same. So that means 0 has to be equal to f of a plus c. So c is equal to negative f of a. So therefore, put it all together, the integral from a to x of f prime of t dt is going to be f of x minus f of a.
Sounds great.
Okay? There's no numbers in here.
I was actually thinking.
We're going to put,
You know that number?
okay.
I just used to use it.
So what we're going to do, and then on Friday, I will formally introduce the fundamental theorem of calculus, and we'll put the two parts together, okay? So we're going to use this formula to evaluate the exact area under the curve of sine of x from 0 to pi. So according to our antiderivatives, what is the antiderivative of sine? Negative cosine. Now I'm going to write it out like this. I'm going to put brackets, and I'm going to put 0 at the bottom, pi at the top. So this means I want to evaluate negative cosine of x. Now, you could have gone negative cosine of x of pi minus negative cosine of x of 0. You could have jumped right to that. But I like to just show this is our f of x, right? This is our original. So now we're going to plug in. So now we're going to plug in negative cosine of pi minus negative cosine of 0. Okay, cosine of pi is negative 1, so we get positive 1 minus negative, so that makes that plus. And then cosine of 0 is 1. Okay, this is a really big conclusion. Why? What did we just find?
The area under the sine curve from 0 to pi is 2.
The area under the sine curve from 0 to pi is exactly equal to 2 square units. Okay. We didn't have a way to find this without calculus because it's not a regular shape. It's not a semicircle, right? So we used integrals to find that exact area. That is pretty cool.
That's very cool.
Very cool.
Did you come up with that?
I didn't. It was like Newton and Leibniz, you know. I wish I could take credit. I wish I could take credit for it, but I didn't. All right, let's do the next one. This is the power rule. 3x squared. What's that become?
3x to the
Cubed over 3. So that's just going to be x cubed. So you can put that in brackets, or remember we used like a straight vertical line as evaluated at. So either one is fine. I use brackets when I have like maybe negative signs or I have more than one term. Okay, so this is going to be 2 cubed minus negative 1 cubed, which gives us minus a negative. Okay, so we should get 9. Again, think about what that means. Here I have a parabola 3x squared. So if I found the area under the curve from negative 1 to 2, that area is exactly 9 square units. Okay?
secant. That's secant.
It's the reciprocal of cosine.
The what?
The 1 over cosine equals
So it's
secant.
like
You know cosine?
our cosine.
Yeah.
No, not arc cosine.
Oh, no.
Arc cosine is cosine inverse.
Yeah.
But
So
secant
It's 1 over cosine. Oh, okay.
is 1 over cosine. Okay, how about the next one? What do we get? Negative x to the negative 2. So that's going to become negative x to the negative 1 over negative 1, evaluated from 1 to 2. So it's just going to be 1 over x. Right? So we get what? 1/2 minus 1. Negative 1/2, which that's fine. We can get a negative. That just means what? The area under the curve,
Mostly down.
it's mostly below the x-axis or all below the x-axis. Okay, secant squared. Not the negative, just regular tangent. Evaluated from 0 to pi over 4. So we have tangent.
Why is it regular tangent, but the other ones didn't cosine is
The derivative of
Because the
cosine is
derivative,
negative sign.
yeah, the derivative of
Derivative of
cosine is negative sign.
positive sign.
Right. If I did the derivative of negative cosine, I get back positive sign. Yeah? Okay. All right. Tangent of pi over 4 is 1 minus 0. So just 1. Did you have a question, Lauren? Oh, okay.
I was telling Jack to calm down.
Did you understand my explanation? Okay. That's the important part. Okay, average or mean value. Okay, so if we have a function that is integrable over the closed interval from a to b, just meaning it has to be a closed. So, yeah, integrable. Okay, the average or mean value is basically dividing the area under the curve by b minus a, or doing 1 over b minus a, the integral from a to b of f of x dx. Just keep in mind, this is when it says average value, we're talking about a y value. Okay. Right, so it's the average function's value, f of x. So we want to find the average value of 4 minus x squared from 0 to 3, and then figure out at what point does it assume its average value. Well, let's just kind of visualize, what does this graph look like, 4 minus x squared? Upside down parabola. Oops. Right, so it's here at 4, it crosses here and here, right? So we want to focus just on 0 to 3. So that would be maybe like that portion. So here's 3.
draw this and we do it, or?
You don't have to. I'm just doing it for purposes of the example so that not just you understand the formula, but you understand what it means graphically, okay? So looking at this, right, you want to think, okay, where's the average value in that region? Okay, so let's do that now using the calculus. So we want to find the average value of f is 1 over 3 minus 0, integral from 0 to 3 of 4 minus x squared dx. So we might be able to kind of guess what it might be, probably somewhere around here, right? Oh. Okay. All right, so what is the antiderivative for 4? 4x minus x cubed over 3. Evaluated from 0 to 3. Okay. So 1/3. So now we're going to plug in 3. So that'll be 4 times 3. That will give us 12 minus, 27 over 3 is 9. Minus 0, right? So that will give us 1. Okay, so our average value, that means The average y value is equal to 1. Okay. Now we want to answer the next part. At what point in the interval does it assume its average value? So how would we find that? Good. So we're going to go back to 4 minus x squared and make it equal to 1. Set it equal to 1, right? So we'll get x squared equals 3. Now, technically, we would get square root plus or minus square root 3, but we just want the positive. And hopefully that does kind of match up. Yeah, right about here. Square root of 3, that's about what, 1.7? That looks right. Okay. And this is just defining it. So here's our mean value theorem. Sure, for definite integrals. So this is just the same thing that we just defined.